I am the Director of Product Management for the Omnicure division. As part of Lumen Dynamics, we were actually purchased by Excelitas last year, but we have about 30 years of experience in developing manufacturing UV curing products. We've been doing both lamp and LED systems. We introduced our first LED system in about 2006. So one of the largest markets that we serve today is the medical device manufacturing market. And what we see today is we have a lot of customers within the medical device manufacturing. They have a process that's set up. It's a repeatable process that's working with their lamp systems. But there's a lot of interest in transitioning that process to an LED curing system. And so we work with these people very closely to make sure that the repeatable process they have with the lamp, they can transition that into an LED system. So when we look at the curing process, whether that be for an adhesive or an ink or coating, we understand that it requires sufficient light of the correct wavelength, that it is absorbed by the photoinitiator, and then if you have sufficient energy, then the cross-linking reaction takes place and you transform the liquid into a solid. When we look at that process in more in depth, what you see is that there's actually a number of different technologies involved in that process in order to get a successful curing process. So you need to take into account things like the photochemistry of the formulation that's being used, the light source that's generating the light, the optics that are being used, how you're going to get that light to your materials, and things you need to be able to measure and control the process, so you need things like a radiometer. And so now when you look at changing one of these technologies, so changing in this case the light source from a lamp to an LED, what you need to take into account is that that's going to have an effect on the other factors within that process. And you need to consider that, again, in order to make that successful transition. So some of the typical applications that we're involved with within the medical device manufacturing, you have things like catheters, syringes, endoscopes, blood oxygenators. Again, all of these products right now are being cured using lamp-based technology. And so what we need to do is, these customers are interested in transitioning to LED, but we need to make sure that they can, again, get a repeatable process using now a different light source. So when we look at why these applications have chosen to go with UV curing in the first place, you look at the benefits you get, things like instant cure, cure on demand, lower temperature curing when you compare it to things like a thermal curing process, and things like energy savings, again, comparing to thermal curing, and environmental benefits, particularly in the materials being used in UV curing, lower VOC content than solvent-based materials. These customers, they're now looking to transition to LED because they can realize even further benefits from their UV curing. So things like lower temperature curing, so the narrow bandwidth of your LED source will allow you to cure with an even lower temperature. And so for heat-sensitive materials, that can be a real benefit in the curing process. There's a potential for lowering your running costs of your process. The LEDs last a lot longer than a typical lamp. There's a lower power consumption for running. So again, you can realize even further benefits from LED. And typically the LED systems can be a little bit simpler to integrate into an automated process. You have very good controls of the LED system. You can have very precise control of the irradiance level for your process. And again, the systems are typically self-contained. They're cooled potentially with air or water, but they don't need any external venting. There's no ozone being generated. So there's certain benefits, again, from integrating the LED. And this is what customers are interested in bringing into their process, but they need to be able to make sure that they don't change the curing process as they're changing their curing technology. So when they look at LED from an environmental benefit, there's some real advantages to LED. Often people have chosen UV curing in the first place. It's considered a green technology with the lower VOC content. And now with LED, you no longer have mercury-filled lamps. There's no consumables, a lot lower energy. So this is one of the reasons people are looking to go to an LED curing technology. One of the biggest benefits of LED, and one of the things most of our customers look at, is the longer lifetime of the LED, and so able to lower their cost of operation. A lot of people I talk to, they think they can get 10, 20,000 hours out of the LED, but one of the things they may not always consider is that over that time, the LEDs are going to degrade. The output is going to degrade over time. The two biggest factors that are going to control the degradation of the LED are the temperature of the LED and how hard the LED is driven. The red curve here shows an example of where an LED is being driven at 100%. And what you see is, even in about the first 500 hours, if you're running that LED as hard as it will go, you can have up to a 10% degradation. Now, 10% degradation, that may be enough to affect your process, it may not be, but it's something that needs to be considered and needs to be measured and accounted for. What we recommend to anybody looking at using LED is if you start out at a lower level, if you start around 75% output, now you start to level off that degradation over time. And so out at 20,000 hours, you only have about 15–20% degradation. And you've also, during that time, you have the ability now to increase the output of your system, compensate for the degradation, and then you have a very repeatable process. Now, since the LEDs are going to degrade over time, that means you need the proper radiometer to measure the output. Now, the LEDs do degrade slower, but there's still a degradation, so in order to maintain that process, you need to be able to measure the output. On the market today now, there's specific technology in radiometry that's designed to measure the output of an LED, and that is different than what is used to measure your lamp-based systems. And so what's important to remember is that the radiometer being used today to measure your lamp system may not be appropriate, may not give you the accurate readings for measuring your LED. So it's important that you, again, in making that transition, you get the right radiometer now to measure your LED. And with the LED being a very narrow spectrum, you need to get, again, radiometers that will be accurate to that spectrum of your LED. When we look at the different cure factors that are affecting the curing process, things like that the light source controls the irradiance level, the exposure duration, and the spectral content of the light. Heat is a byproduct of the reaction, but it's again something that can be controlled by the curing process. So these are things that we need to take into account from the light source. When we look at irradiance, the radiant power that arrives at a surface per unit area. Now, everybody I think understands that we need sufficient energy to convert the photoinitiator to start the reaction. But one of the things you can also have is you can have excess energy. You can have too high in irradiance, which can have a detrimental effect on the curing of your adhesive. And today's LED systems, you have 8, 12, 16, up to 20 watts per square centimeter in irradiance. So you have very high irradiance levels available. So you need to be able to measure and also then adjust and control the irradiance level so that you can set the irradiance level of the process as to what's appropriate. Most of the LED systems or some systems on the market may give you the irradiance value at a 0 millimeter working distance, or right at the face of the LED system. What you really need to keep in mind is the irradiance level at the working distance you have. So what's the irradiance level that your parts are seeing? And that's really the key, and so that's got to be the importance of what you're measuring. Because what happens with LED systems is the irradiance level on the LED systems tend to drop very significantly over working distance. Now there's ways that you can improve upon that. For example, you can use optics to improve how the irradiance level holds up over working distance. But you need to know then what that level is at your parts, at your specific working distance. And just to give you an example of some of the benefits that you can get from using specific optics, what this shows here is that two LED systems, they start out with very similar irradiance levels at a 1 millimeter working distance. This system here includes a lens. This system does not include a lens. So at 1 millimeter, you have 8 watts per square centimeter and 9 watts per square centimeter. So very similar output. But as you start to increase the working distance, and you get to about a 20 millimeter working distance, which is a very typical working distance for an application, you can see that without the lens, the 8 watts per square centimeter has now dropped down to 1.5 watts per square centimeter, so a very significant drop. With the lens, you've still dropped from 9 to 4.5 watts per square centimeter, but what the optic has now allowed you to do is maintain a much higher irradiance level over that working distance. And what optics will also allow you to do is you can focus in your working distance and your lens to match that working distance. So it gives you that flexibility to really maximize the irradiance level for the working distance of your application. So that's one way to really improve upon the irradiance maintenance of your system. Certainly one of the biggest differences that you see when looking between LEDs and lamps is the spectral output of the systems. So the blue chart here, that shows a typical spectral output of a mercury system. In this case, there's actually a filter in the system, so it's 320 to 500 nanometers. The small curves here, that's a typical LED system. So these are examples of 365, 385, and 400 nanometer LEDs. Now, one of the things we see is a customer has a curing process. They've set 5 watts per square centimeter as their irradiance level using their lamp-based system. And what you get then at 5 watts per square centimeter on a lamp system, you get a large chunk of UVV, a nice big chunk of UVA, and potentially a little bit of UVB and UVC content that is curing your material. If you now switch to an LED, so if you now set your process to that same 5 watts per square centimeter using an LED, a 365 nanometer LED, you're now exclusively giving energy 5 watts per square centimeter of UVA. Same as if you use a 400 nanometer. Now you're giving exclusive energy in the UVV spectrum. And so potentially you're going to end up with different results because that mix of energy is no longer the same as it was with your lamp system. So that needs to be tested to see what's going to happen with your adhesive. So when we talk about the spectral content, the correct wavelength, you need sufficient light of the correct wavelength to match up with your photoinitiator to get a successful curing process. With a broadband lamp system, it's much easier. You have a broad spectrum of light, so it's easier to match the output of your lamp system to the absorption requirements of your photoinitiator. With an LED where you have a very narrow spectrum, now it's very critical that you match up that narrow spectrum of LED with the absorption requirements of the photoinitiator. If those two don't match, it doesn't matter what your irradiance level is, you're not going to get any curing. And so for this reason, most LED systems offer different options and wavelengths that helps you to match that up. So there may be 365, 385, 395, 405 LED wavelengths available, and that's going to make it a little bit easier to match up the output of your LED with the requirements of your photoinitiator. So while the broad spectrum of the lamp makes it easier to match up with the requirements of the photoinitiator, one of the problems that a lamp system can bring is that you have excess or unnecessary wavelengths. And those wavelengths may be absorbed by different components within the adhesive. They may be absorbed by the materials being bonded together, and that can generate heat. So even though UV is typically a low heat process, if you have excess wavelengths, you can start to have the absorption of those energy, generating heat in your process. The narrow spectrum of the LED really helps to improve upon that. And so you have the potential for a much lower temperature curing. So with the lamp-based systems, what we can do is we can introduce filters to filter out some unwanted wavelengths. And that, in this chart here, is an example where we introduced a cooling filter and we were able to reduce the temperature. However, with LEDs, because of the very narrow spectrum, you get a much, much lower curing temperature. So we have multiple wavelengths available. Which one is right for your process? There's different ones to choose. So many formulations that we run into, they'll specify 365 nanometers as the wavelength. A lot of that is historical based on the formulations being set to match the 365 nanometer peak of the mercury lamps. But what we've seen in our testing is that many of the free radicals will cure with wavelengths above 400 nanometers. Many of the cationic photoinitiators, though, tend to cut off at 380 nanometers and below, again, somewhat limiting the LED available for curing them. In general, 400 nanometers tends to provide a better through cure, where the 365 nanometers generally provides a better surface cure. And then when we look at the LED systems, 400 nanometers, 395 nanometers, they generally have significant higher output than 365 nanometers. So these are all considerations to take into mind when you're trying to select what is the most effective wavelength for the curing process. One of the important things that you also need to keep in mind are the parts that are being joined together and the materials that are being used. The absorption of those materials can have a significant effect on how your process, the success of your curing process. Now, when you're using a broad spectrum lamp, even if the material is absorbing some of the wavelengths, you may be getting enough of the other wavelengths through the material to the adhesive and getting a successful cure. But now, if you're moving to a narrow bandwidth LED, if you're getting absorption at those wavelengths of your LED, it can have a very serious effect on the success of the curing. So this is an example here of a customer who was joining two plastic parts together. The adhesive specified 365 nanometers for the application. So they were trying out a 365 nanometer LED, but not getting the successful curing that they were hoping for. We took a look at the material they were bonding, and what we found is that the plastic parts themselves strongly absorbed at 365 nanometers. And so 50% of the energy was never getting through the material to the adhesive, and that's why they weren't getting a successful cure. When you look at the absorption curve, right here, what you see is when you move up to 395, 400 nanometers, you're now getting about 80% of the energy through the material, so only 20% absorption. And so now you're getting a much more efficient use of your light energy. The material still cured well at 395 nanometers, so in this case, even though the adhesive specified 365 nanometers as the wavelength, we actually got a faster cure with lower heat using a 395 nanometers. So again, you always need to consider the parts that are being involved in curing in order to get that successful curing process. Another thing to keep in mind is that many of the adhesives might have multiple photoinitiators, and that's designed to match up with the multiple peaks from the mercury lamp. So now what happens when you take an adhesive that may have multiple photoinitiators and you use a narrow spectrum light source to cure it? Is it going to be as successful? So we did some testing on this, and where we took a number of different adhesives and we cured them with both a lamp and an LED to compare the results of the cure. For many of the adhesives, we would achieve pretty much equivalent results. An example, though, for one adhesive where we found an interesting result was we took the adhesive and we exposed it to 5 watts per square centimeter for 5 seconds with both a lamp and an LED system. And one of the ways that a quick way we use to measure to see whether an adhesive is cured is to measure the micro hardness of the adhesive. It's an indirect way to see whether it's cured. And in this case, they both had a similar micro hardness reading, which would indicate that they were cured almost equally. However, when we started to do further analysis into the material and we used a DSC to actually look at the uncured material, what we found is that the adhesive that was cured by the LED actually had significantly more uncured material than the adhesive that was cured by the lamp system. Now, we weren't able to tell what that material was or what the effect would be, but in this case, the question is whether or not the material cured with LED was cured as well as that cured with the lamp. And that's one of the questions that needs to be answered within the curing process to make sure that when you make that transition, you're getting the equal results that you were with the lamp-based system. And so what this shows is that further analysis is needed in order to ensure that that is a successful transition. And the last thing I'm going to talk about now is surface finish. So one of the things we see, free radical adhesives, they're susceptible to what we call oxygen inhibition. So even though the adhesive may be cured, you end up with a slightly tacky surface on top. And that's where the oxygen prevents full cure from that top layer of adhesive, and it ends up a little bit tacky. Now, there are some specific formulations available that help to minimize the tacky surface, but there's also ways within the curing process that you can help to minimize the tacky surface and help to get a nice hard surface finish. So there's things like a nitrogen purge can be used where you eliminate oxygen, and that is one way to get a very nice hard finish. Things like high picoradiance or heat are other ways that you might help to get a strong surface finish. Another very common way of doing it with lamp-based systems is to also add a bit of UVB and UVC content. And the UVB and UVC really helps to give you a better surface finish. Now this is great when you're using a lamp system where you have those wavelengths available. Unfortunately with LED, really the lowest wavelengths that are commercially viable today is about 365 nanometers. So while we have a number of people working on some UVB and UVC LEDs, they're not really commercially viable today. So if surface finish is an issue in your process, and if trying to get a nice hard surface finish is something that's a concern, then LEDs mean you need to put something else in your process because you don't have that option of using UVB and UVC to get that nice hard surface finish. So in summary, we have, again, a lot of our medical device customers, a lot of people looking to potentially transition their process to LED. The benefits they can see, things like lower heat in their curing process, lower cost of operation, some of the environmental benefits that LEDs bring to their process are things that can be very beneficial, and they've generated a lot of interest in customers potentially transitioning to LED. Some of the challenges that you need to be aware of if you are looking at this transition, though, is things like making sure you have the proper radiometry. The adhesive compatibility must be taken into account, the differences between the lamps and the LED systems, and surface cure. Surface cure, again, may be an issue if you're switching from a lamp system to an LED. So always keep in mind when you're changing the lamp source, you really are changing your curing process. And so the only way you can be sure that you can maintain a repeatable curing process is to do the testing and ensure that you are able to get that process repeatable and controlled. And thank you. So any questions? Typical what we see on an adhesive, for example, is you could get yellowing of the adhesive. The adhesive can get brittle and hard, so you can reduce flexibility on the adhesive. Those are sort of some of the common results when you're curing too fast. Particularly, the yellowing is one we see where you could actually start to burn the adhesive. Increased outgassing is another problem from too high of an irradiance level. Yeah, that is one of the things we've tested, and that can actually have some real benefits to curing, maintaining a lower heat, maintaining lower temperature in the process. With the pulsing of the LED, which is something you can't really do with a lamp system, the LED allows you to turn the system on and off really as quickly as you want, almost. So the pulsing can definitely have some benefits, and what we've seen is you can help to use a higher irradiance level and still maintain lower heats by doing some pulsing of the LED. Yeah, again, from our experience, we haven't seen those types of results. It's really possible. It depends on the material that you're using. And again, the testing is what is going to determine it. Some of the applications where we use the pulsing, the ones it wasn't necessarily in an adhesive process. And so the key for them was really maintaining that low temperature. And so the pulsing helped to do that. But it wasn't a question of a bond strength of the material that was being used. High peak irradiance can help to speed up the curing process and really help to overcome that oxygen inhibition. So that's just one of the ways some of our customers have tried to improve upon that by really just hitting it with a high burst of irradiance to try to improve that. It doesn't always work. It's just one of the ways customers have tried.